In this video, I'm extending the explanation on the stationary wave in air column. Here, we will talk about how the frequency of the harmonic modes are differ from each other. Okay, so we are going to derive that. Okay, it's a painful process, but after you understand that, you don't have to repeat that when you answer the question in the exam. Okay, because we need to use a faster way to answer instead of deriving the frequency of the next harmonic. Okay, so let's start here. Just now we talk about closed pipe in the experiment, and then I say that you can also form stationary wave in open pipe. So open pipe means both end open. Closed pipe means one end open and one end closed. So what you see below here under each of these pipe is their different harmonic. So the first one is the fundamental mode. This is the fundamental mode. This is the first overtone. This is the second overtone, and so do the one on the left hand side here. Okay, but we don't call all of them second harmonic and third harmonic and fourth harmonic. So I'll introduce the term later. It's a bit confusing, but bear with me. Hold on. Right, so for the open pipe, the first harmonic here, I will start off with the open pipe because the closed pipe and the string that fixed on both ends, I need you to do that on your own. I'll give you more instruction later. So let's start off with this, that we have V equals to F1 lambda 1. Okay, if you hear a loud sound for this, at the fundamental mode, then its frequency will be F1. The wavelength from inside there is lambda 1. Okay, the tube is all the same throughout the three modes here, and this is the fundamental mode. This is how it's going to form. Both ends must be antinode, and then inside here there will be a node, and from here we can identify that okay, this is actually half a wavelength, because you can imagine that you need this part to complete that. Okay, that's then only it become two loops and one wavelength. So between two antinode is just half a wavelength. Okay, between two antinode is just half a wavelength. Yeah. Okay, let me erase this part a bit. Oops, sorry. Okay, because I need the space here. Okay, so now if I change the wavelength into length, then I should get like one wavelength equals to 2L. Okay, let me change this one first. So it become 2L. Okay, because half a wavelength is L, so therefore wavelength is 2L. Okay, so let's say I go on to the next harmonic, then I get it at frequency 2 and lambda 2. Okay, and the speed here is a constant. This 2 here, the speed here is constant because it's the same wave, so it travels at the same speed. And F2, for this case, if you look at the pattern here, we have 3 antinode, right? So this one, if you look at the pattern there, it should be one wavelength. Okay, so this is equivalent to one wavelength. So wavelength 2 equals to L. Okay, wavelength 2 equals to L. So if I want to get back the speed similar to the one at the top there, what I need to change for the F2 is, because I want to get back the same thing, right? So what I need to change for the F2 is I must change it to 2 times of F1. I must make sure that the F2 is 2 times of F1, then only I'll get 2F1L, same as the one on top here, 2F1L, which means that they are the same speed, right? So it means that F2 must be 2F1. Because it's 2 times of the fundamental mode, we call this the second harmonic. Okay, this is the second harmonic. If let's say we found that the first overtone is 3F1, then we have to call it the third harmonic. We cannot call it second harmonic. The harmonic, the term, right, it depends on how higher is the frequency compared to the fundamental mode. Okay, so let's see. And then next one, F3, lambda 3. Then we have the lambda, we change into length, so now it should be a bit more skillful. So we have one wave plus half, so it will be 1.5 wavelength equals to 1.5 lambda equals to L. Therefore lambda will be equivalent to 3 over 2 over 3 L. Okay, because 3 over 2, this is 3 over 2, 3 over 2 is 1.5, so 3 over 2 wavelength equals to L. Therefore you bring the 2 up, bring the 3 down, 2 over 3 L. Okay, so you get 2 over 3 L as the wavelength. How are you going to make this the same as the wavelength, the speed? First thing here, 2 F1L. So how should we change the F3? Okay, we should change it to, we should use 3 times higher than the first harmonic frequency. Let's say it's 50 as the first harmonic frequency, then this one should be 150. Okay, 3 times higher. Therefore, because of F3 equals to 3 times of this, so we call this the third harmonic. Okay, we call this the third harmonic, right? So I want you to do on your own for the closed pipe. Okay, for the closed pipe, you get this as the third harmonic, I can tell you first, and then you get this as the fifth harmonic. Okay, I need you to show the derivation just like show for the open pipe. And then on the right hand side of the open pipe, on your handout, you have some space there. You draw the 3 cases for the 2 end fixed string, and then you derive their frequency also. Okay, you derive the frequency, so that will be your homework. Yeah, so I'll end this video here.